Welcome back to the Explainer. Today we're unpacking a massive piece of Unit 5's foundational soil physics, Darcy's Law. If you've ever caught yourself wondering how engineers actually figure out what's going on with water hiding deep underground, well, you are definitely in the right place. But before we jump straight into the math and those Unit 5 equations, let's start with a really big question, one that civil and agricultural engineers tackle literally every single day. How do we predict the hidden movement of water deep beneath our feet? I mean, it's not like we can just look at a river and measure its speed, right? This water is locked away inside rocks and dirt.
So here's our roadmap for today. We'll start with the movement of soil water, decode Darcy's law, translate that into math, check our assumptions, see exactly where the law breaks down, and finally, look at some major real-world applications.
All right, Section 1, the movement of soil water. Let's lay the groundwork.
Okay, everything really starts with understanding that soil and rock aren't entirely solid. They're what we call a porous media, which just means they contain tiny pores, or voids. And that brings us to a supercritical concept, permeability. Basically, this is a material's ability to allow fluid or gas to pass through those voids. Think of it kind of like a giant rocky sponge. As long as the pores are connected, the fluid can move right through.
Now notice the specific condition we're looking at here, saturated flow. This happens when all the pores in a media are completely filled with water, which keeps the water content constant over time. And here's the kicker. Darcy's law was specifically developed to govern this exact state of saturated flow.
Moving right along to Section 2, decoding Darcy's law, the core principle.
Take a look at this block representing a soil matrix. It brilliantly illustrates what the French engineer Henry Darcy actually discovered. You can see water entering from the top at a higher elevation, so a higher potential head, and exiting down at the bottom, which is a lower potential head. Darcy experimentally proved that water flow through completely saturated sand is directly proportional to this hydraulic head difference. The water is literally just falling from a high potential to a low potential. To put his discovery into a more formal definition, it goes like this. The rate at which a fluid moves through a permeable medium is directly related to the difference between vertical elevations and indirectly to the distance. In plain English, this foundational law just means the flow is driven by pressure differences and how well connected the rocks or soil are. If the total potentials are equal across a distance, absolutely zero movement is going to happen.
Which brings us to Section 3, the math behind the flow. Time to translate that physics into equations.
So, the crucial step here in Unit 5 is how we translate these physical observations into math we can actually use. Here's the primary equation for the volumetric flow rate of water, represented by Q. Now don't let the variables freak you out, it's actually pretty elegant. The total flow equals the material's saturated hydraulic conductivity, that's K sub S, times the cross-sectional area A, all multiplied by the hydraulic gradient, I. Oh, and notice that negative sign? It's just there to show the direction of the flow, confirming water naturally moves from a high potential area down to a low potential area. A lot of times, we actually want to look at the speed of the water rather than the total volume. And that is where Darcy's flux comes into play, represented by a lowercase q. We use this flux to separate the total volume of water from the specific speed of the flow through a single unit of area. It's kind of like the difference between asking how much water is currently in a pool versus how fast the garden hose is actually filling it. By taking the total flow Q and dividing it by the area A, we get a value expressed in depth units per time, like centimeters per second. So it tells us exactly how fast the water is moving through a specific cross-section of the soil. But of course, water in the real world doesn't just travel in a straight, boring line. It moves in 3 dimensions. Luckily, Darcy's law gracefully scales right up to 3D by combining the partial derivatives of the flow along the x, y, and z axis. And here's a really cool part. If the soil is isotropic, meaning it behaves the exact same way in all directions, these 3D equations beautifully simplify our calculations. We can just factor out a single hydraulic conductivity value for the entire mathematical model.
All right, Section 4, assumptions and validity. Let's go over the rules of the road.
When formulating all this, Darcy had to lock in some very specific conditions. These 5 core assumptions act as a strict checklist that absolutely must be met. 1. The flow has to be laminar, so smooth, not turbulent. 2. Water and soil are treated as completely incompressible. 3. The soil must be fully saturated. 4. The liquid flow has to be steady. And 5. Standard testing temperature is assumed to be a nice 27 degrees Celsius.
When those assumptions are actually met, the law guarantees some incredibly predictable properties. First, a zero-pressure gradient guarantees no flow. We call that a hydrostatic condition. Second, if there is a pressure gradient, the flow perfectly tracks from high pressure to low pressure. And mathematically speaking, a steeper or greater pressure gradient will always result in a much faster discharge rate. Basically, because of these strict assumptions, groundwater predictably follows the path of least resistance and the highest pressure drop.
Now for Section 5, where the law breaks, understanding the boundaries. Because physics is rarely perfect in the wild, right? Notice the physical limit of the law here. Darcy's law requires laminar flow. In fine-grained sediments, stuff like clay, silt, and sand, the gaps between particles are incredibly tiny, which keeps the water flowing smoothly in parallel layers. So the law applies perfectly. But in coarse-grained sediments, like gravel and cobbles, those gaps are huge. The water starts to swirl, it churns, and it becomes totally turbulent. Under those conditions, Darcy's law completely fails.
We actually quantify this threshold using something called the Reynolds number. For fluid flowing through standard circular pipes, flow stays laminar until a Reynolds number of about 2,000. But soil is infinitely more complex than a smooth pipe. For Darcy's equation to safely apply to sediments, the flow must maintain a Reynolds number less than or equal to exactly 1. Yeah, let that sink in for a second. From 2,000 all the way down to 1. Anything higher than that and you risk entering a turbulent regime where the math just no longer accurately predicts the flow.
Furthermore, Darcy's hydraulic conductivity assumes the fluid's viscosity remains constant. This works great for standard groundwater streams where temperatures barely change across an aquifer, but it brilliantly illustrates why the equation needs heavy modifications if you're dealing with, say, hot oil pushing through deep reservoir rocks. If the temperature fluctuates wildly, the viscosity changes dramatically, and you simply can't apply the standard Darcy equation without making some absolutely crucial adjustments. Finally, Section 6, Real-World Applications. Why all of this actually matters. Far beneath the surface, these distinct geological sedimentary layers, the shelves, the slopes, and the plains, are exactly where Darcy's theoretical math meets physical reality. Engineers don't just look at these layers as rocks, they see them as massive, interconnected fluid transport systems.
And these applications are absolutely critical to modern civilization. We use Darcy's law to manage groundwater flow, making sure we aren't accidentally depleting natural aquifers or contaminating underground streams. It's also a major standard in the petroleum industry, used to assess and calculate the recovery volumes of oil, gas, and water from conventional reservoir rocks. So, by mastering these concepts in Unit 5, you aren't just memorizing formulas to pass a physics test. You are gaining the exact tools engineers use to secure city drinking water and extract global energy resources.
So as you wrap up your review of Unit 5 and practice these formulas, keep this real-world application in the back of your mind. How will mastering the invisible physics of underground fluids shape the way we manage the Earth's most critical resources tomorrow? That is the real power of Darcy's law. Thanks so much for joining me for this explainer, and I'll catch you in the next one.